In this video, we're going to start talking about the third case for calculating the change in enthalpy and change in internal energy, which is the phase change, which is either melting, freezing, condensation, evaporation, whatever the case that we have. So this is something that's going to be very easy compared to what we covered before. To kind of refresh our memories, I would like to revisit this slide. We have seen this slide more than once before. And this was demonstrating the steps by which the material passes by, starting from being solid until it reaches the vapor phase. And we said it will take some sensible heat and then to turn into a solid that is about to melt, and then will take latent heat and so on. And we in this part, we are interested in these two cases of the evaporation or melting. And as we said before, evaporation or melting are called latent heat because they happen, but I mean they happen at constant temperature. So it's solid at 0 Celsius turns into liquid at 0 Celsius, or liquid at 100 Celsius turns into vapor at 100 Celsius, or whatever the boiling point is. So to know how to calculate the latent heat, it's going to be very easy. We are not calculating anything. We are extracting data from tables. So if you remember, for example, if we are dealing with water, we had the saturated steam tables. We had, for example, this pressure table. We had the saturation pressure, the saturation temperature, the saturated liquid specific volume, the saturated steam specific volume, the same for internal energy, and the same for enthalpy, for specific internal energy and specific enthalpy. But here we had one extra column, which is the evaporation. And this, as we said before, this is the difference between the enthalpy of saturated steam and the enthalpy of saturated liquid water, which is the latent heat. So in this case, you can find the latent heat of vaporization directly, if it's water, of course, by going to the steam table and finding this delta H of vaporization, which is the difference between the saturated liquid and saturated vapor specific enthalpies. One thing to notice here is that the latent heat is a function of temperature. As the temperature increases, the latent heat decreases. So it's not constant. It's a function of temperature. So this is something we need to keep in mind. So in case we have steam, we need to know, or water, we need to know the pressure and temperature at which the evaporation takes place, or at least one of them, because we can find the other by the knowledge of one. So this is the first table that we can find the specific enthalpies in. The second is the table B1, which is the table that we used before to find the specific gravities. We visited this table before. The part of interest here is going to be this column and this column, which are the heat of fusion or the heat of melting. If you mean it can be mentioned or named the two names. And the second is the heat of vaporization, which is this column. So it's as simple as picking the numbers from the table. There are a couple of things we need to notice here. First, compared to the steam table provides the information of the enthalpy or the latent heat as well, would be in kilojoules per kilogram. In case of the table B1, we have the latent heats, still latent, a specific enthalpy change due to the phase change. It's in kilojoules per mole. So we need to be careful about dealing with the numbers. It's not just a number, it's a number with the units. We need to make sure that we understand the units, so we make sure that the units are homogeneous. So this is the first thing. The second thing is that we have the column before here and here is the melting point and the boiling point. It's clear, and it says it's in Celsius, and this is in Celsius. The second thing is that we have only one value for the latent heat. In the previous table, we had many values for the latent heats depending on the temperature and the pressure. But here we have only one value, and this is because what is written here, it's the heat of fusion. This is the footnote here. C is the footnote that this is the heat of fusion at Tm, which is the melting point, the normal melting point. And this is going to be, if you check the footnote for letter B, it's going to tell you that this is the normal melting point. And it's meaning it's the melting point at 1 atmosphere. The same here, this is the boiling point under a pressure of 1 atmosphere. So this is the condition of melting point and the boiling point. And this is the value of the melting or the latent heat of fusion and the latent heat of vaporization, but this value is at the melting point, the normal melting point. This is at the normal boiling point. So this is important, and we need to be careful about this as well, because the value varies, so we need to plan accordingly. So this is all what we need to know. In the textbook, there are some sections discussing the prediction of the latent heat of vaporization in case of having a material that's not listed in the table, based on the shape of the molecule and its structure and different things. So it's there in the textbook. In case you're interested, you can check it. For now, we're not going to cover this. We just go with the tables. So let's take a look at this example. It's going to be a nice example here. So it says, at what rate in kilowatts must heat be transferred to a liquid stream of methanol at its normal boiling point to generate 1,500 grams per minute of saturated methanol vapor? So we have liquid methanol at its normal boiling point, meaning that it is saturated liquid, and it is transferred to saturated vapor by heating, and we know the molar flow rate. So since it's saturated liquid and turning into saturated vapor, so it's only acquiring latent heat. So the first, we start with the energy balance equation, which will reduce to Q equals delta H. We will cancel the work, because there is no work here, it's just a heater. We don't have any change in kinetic and potential energy because we don't have any information, so we'll ignore them. We'll assume they are zero. So delta H is going to be Q equals delta H, which is N dot multiplied by delta H hat. And we know delta H hat is the latent heat of vaporization, because it's turning from saturated liquid into saturated vapor. So we need to adjust the units. Again, the units of this term, kilojoules per mole, and what we know here is grams per minute. So you'll divide this by the molecular weight. So it's going to be gram mole per minute, or moles per minute. When we multiply by the specific enthalpy of kilojoules per mole, now the units are matching, and we can calculate the value to be kilojoules per minute, and we divide it by 60 to be in kilowatts, as it's required in this problem statement. So and as you see, this value of delta H of vaporization is just picking this number here. There is one thing that needs to be mentioned here, which is regarding the sign of delta H. So if the delta H that we have here is for melting and for vaporization. If we have the opposite, and for example, if I have a material that is condensing or freezing, in this case I'll use the same value. Of course, it's under the same pressure and temperature. I'll use the same value, but with a negative sign, because in this case the heat is being removed from the material, not absorbed by it. So this is the only difference if we have freezing or condensation. So this is all for now. Next time we will take another example. This next example will be very useful, because we are going to combine different things. We are going to combine the effect of temperature with the effect of pressure with the hypothetical path. So now we will put the pieces of the puzzle together. So we'll see you then, inshallah. Goodbye.